All right, welcome everybody to another stream. Today is going to be a little bit different than previous weeks because today we are going to do something that's more on the advanced side of Rust. This hopefully will be useful for those who are in the kind of intermediate going on to advanced phase of Rust, but also for those who are more in the beginning side of things as well. What we're going to be doing today is not necessarily something that you're going to do in many or most or even any of the Rust projects that you'll end up writing. But because of the nature of what we're doing, you have to really have a good understanding of how Rust thinks about memory, and in other words, Rust's memory model. So what are we going to be doing today? Well, let me switch on over to the screen here. Today we're going to be building our own version of vector. And what we're going to be doing in order to do that is really touching a lot of different things in Rust, including a lot of unsafe, because we're not going to be using, obviously the easiest way to do this is to just kind of write a new type, a wrapper around standard vector, and then we would be done very quickly. But we're not going to be using vector. We're not going to be using vec in the standard library. We're not going to be using box. We're not going to be using anything like that. We're going to be using kind of the plain allocation API that Rust comes with that you normally don't have to use at all. And touching a bunch of unsafe types in order to build up a safe vector abstraction. We're going to be looking a little bit about, it's probably not going to be nearly as efficient as the standard library vector. There's a lot of different things that have gone into vec over the years in order to make it super efficient and also compile fast and be efficient also in disk space in addition to runtime performance. We're going to be doing this roughly as easily as you can. And doing some tests to make sure that our vector implementation actually works properly. All right. Let me know if you have any questions as we go through this. We will be taking this slow, but again, this is definitely an advanced topic, so there are some things that probably will not make sense to some in chat today, watching today, and in the future on YouTube. Also, I almost guarantee that we'll end up making some sort of mistake today that and exposing some kind of undefined behavior that our vector should work for at least the test cases that we're using, and there shouldn't be hopefully anything obviously wrong with it. But unsafe can at times be quite difficult to get exactly right. I'm, especially when people are watching me, I don't doubt that I'm going to end up making some mistake. So keep me honest, chat. Today we'll try and get through this. Also looking over, besides the documentation for vec, which will come in handy for us to know how we can kind of build up the same API that vec has. I also have open here the implementation for vec in the standard library, and if we have time or interest, we can go through and look at that. And along with that is also the real bones of vec, which is raw vec. Vec itself is really just a small wrapper around raw vec, which does kind of, this is not a public API, this is just an implementation detail. But raw vec is the bones of vec, and also dec vec as well. So we will probably end up taking a look at that as well. All right, I've been blabbering too much. Let's go ahead and get started real quick. So the first thing to do, and let me go ahead and make this a bit bigger here for everybody. The first thing to do is start a project. So we're just going to go cargo new, and then I'm going to call it myvec for now, and I'm going to make it a lib. And then I'm just going to open this up in VS Code for now. All right, let's bring this down a little bit. And let's see if I can make this a tiny bit bigger, just so everybody can see the screen properly. And let me know if I should make that larger or anything like that. We we can change things as we go along. And in fact, we can just close that because we will only be doing one file today mostly. All right. Cool. Yes, welcome everybody. Very excited to be here. Hello. Great. Okay, so let's go ahead and get started by writing a test. The first thing that I want to do is write a test that works for the regular standard library vector. And so we can go ahead and say let vec equals, and then we'll do vec new, here. And then we can do, oh, and I forgot to make it mutable. We got to make it mutable because we're going to be pushing something onto the vector. And we can say vec push here, for instance, and let's just go ahead and push on, let's go ahead and make these usizes. So we'll push on 3 numbers here. And then I want to go ahead and assert equal that vec's capacity is going to be equal to 4. And of course, this is a macro. It's got to have that nice exclamation point there. And vec's len is equal to 3. And we'll just do this for now. We're going to be adding to this test as we go along. Let's go ahead and run this real quick with cargo test, and hopefully it passes, and it does. Cool. So this is the first thing that we need to know about vector. If you've used vector at all, you might have come across this before, that that vector has a difference between its capacity and its length. The length of the vector is, as you would expect, the number of elements that is inside of it. And so we have 3 elements in here, and I'm just going to change this to 2 and 3, and we can get rid of these as well, just to have different elements in there. The length is the number of elements in here, in this case 3, while the capacity is the number of elements that could fit on the heap allocation that vector has made without causing a reallocation. And so presumably we can go ahead and push one more item onto this vector before a new heap allocation is made. And in fact, let's go ahead and test that real quick. We'll push on 4, and then we'll push on 5. And what I believe will happen is that vector's capacity will go up to 8, because I believe the way that currently it works is that every time you reallocate onto the vector, it doubles the size. And the length will be 5 here. So let's go ahead and run that real quick, and it passes as well. So we've confirmed here that every time you go over the capacity of the vector, it will double its size. Or I don't know if we've confirmed every time, but I believe that's how it works, and that's how our vector will work today. There's a question from chat. The first push element type implies the type of the overall vector. Exactly. So we have explicitly said for this first element that 1 is of type usize, and that has made here that our vector is a vector of usizes. And of course, if we go ahead and change that to isize, you can see immediately right here that updated to a vector of isize as well. And because these numbers down here don't have explicit type annotations on them, they kind of just go along for the ride and end up becoming the right type depending on whatever they need to be in order for this thing to compile correctly. Cool. And then there's a question of whether we'll benchmark this implementation. That could be fun as well. Let's see if we have enough time. I have at most 2 hours today. We'll see how far we get along today. I imagine that my implementation will be much slower than, I'm not. I wonder if it will be slower. It may end in the cases that we would test for. It may actually end up being roughly the same, because vec is actually pretty simple at the end of the day. We'll see. That could be very interesting. All right, cool. So let's go ahead and start implementing it. So I'll go up here and say we're going to have a pub struct. Let me go ahead and close the terminal there, and I'm going to call it my vec here. And then we have to decide what my vec will contain. And I'm going to base it off of the implementation in the standard library. It's basically going to have 3 fields on it. A pointer here, and this pointer is going to be a pointer to the first element in the vector. All right. And how do we want to model this pointer? I'm going to model it as a non-null raw pointer, essentially, which we can get from use standard pointer non-null here. So this is going to be non-null of t. And so my vec is going to be a my vec of t, any type t here. Let's pop on over real quick to the documentation here and take a look at non-null, because this is important. So most of the time we're not dealing with raw pointers. You only end up dealing with raw pointers if you need to use unsafe for kind of building these low-level abstractions. Non-null is like a raw mutable pointer, this star mut t, but it's non-zero and it's covariant. The first one is important in that it can never be 0, so this thing can never be null. And it's covariant. What covariance means in this case is not necessarily important. The most important part is actually in the documentation here. Usually it's not necessary to go against the covariant nature of non-null. Covariance is correct for most safe abstractions such as box, RC, arc, and vec. So we don't have to worry about that. There is a great article or it's not even an article. Let me see if I can find it. I'll post it afterwards. It's by Rain. And they made an article about covariance that does a really great job of explaining what covariance is and contravariance and stuff like that in terms of Rust and in terms of Rust lifetimes as well, which is really great. So I'll link to that after this. Cool. Chad is asking, is it possible to use box slice t instead of raw pointers in an n? It's probably possible to use box slice t. I explicitly don't want to use slices for the implementation. So box slice t is not possible because you need some of the elements to not actually be initialized. So it would have to be box slice, maybe uninit t. Oh, I see that. You actually wrote that underneath. It would definitely have to at least be that. That probably could work, although you have no way of actually allocating that space. So you would first have to allocate. I'm not sure if it's possible. I haven't tried it myself. Maybe it is, but I'm not sure. It's definitely probably going to be easier with raw pointers, but yes, you end up having you end up having to use unsafe then instead. And then Chad is also talking about what covariance means, how covariance deals with inheritance oftentimes. Most of the time, Rust does have an inheritance, but inheritance of lifetimes. So normally this comes into scope when you're talking about lifetimes and stuff like that. That's a little bit out of scope here because we can just assume that unsafe will do what we want. Non-null will do what we want. All right, back to the code. So we're going to have a pointer, and then we're going to have a length, which is going to be of type usize. And we're going to have a capacity. And we already talked about what these are. Again, length is the number of elements that are initialized in the vector, and capacity is the space on the heap that is kind of allocated there for use. And once we pass the capacity, we'll have to resize the vector instead. Great. So then this part becomes pretty easy. We can go ahead and do impl my vec t here and implement the new function. And new is going to return self here. And this is all pretty straightforward. Obviously, len is going to be 0, and capacity is also going to be 0. This is how the vector in standard rest works. When you create a vector with nothing in it, it does not allocate. So the capacity is 0, meaning there is no space allocated on the heap for this vector. It's at this point completely kind of stack allocated with no space for any elements at all. But then that lends to the question of what will pointer be? How do we go ahead and get a non-null pointer here? Now, if we were using raw pointers, we could probably just go ahead and stick in a null pointer here. Or with non-null, the great thing that you can do is you can, if you want to kind of mimic nullable pointers with non-null in a somewhat more verbose way, you can do option non-null. And this has the advantage, obviously, of if you have a null pointer where option is none, then you can't accidentally treat it as if it were an initialized pointer. So this can also be useful, even if the pointer can be null, to still model it as option non-null t. But we are explicitly modeling it as this, in that it can never be null. Luckily, if we go over here to the documentation, the very first function for non-null here is dangling, which creates a non-null pointer that is dangling. So it's not null, but it's dangling. And it's funny enough, it actually mentions vec_new as the use case for this. That's pretty easy. We're implementing vec_new here. This is, it's useful for initializing types which are lazily allocated. So we have some pointer. It doesn't currently actually point to anything. It's kind of dangling out there, but it is not null. So it's not been 0 initialized. It's effectively set to random. Great. So we can go ahead and do non-null dangling here. And what this means is we have our first kind of invariant that we have to keep in mind, is that when capacity is 0, the pointer is going to be dangling and we shouldn't use it. So non-null is allowed to be dangling, that's totally fine, but it means that we can't use it unless we first initialize it to something actually real. We know when capacity is 0, that non-null will be dangling, so we need to always keep that in mind. Is capacity 0? If so, don't use pointer. That's kind of rule number 1 that we'll have to establish. And we can go ahead and make this pub here. So now we have a way to initialize our vector, and in fact, if we come down here to our test, and in fact, let's go ahead real quick and color these in here and say use super. So we're bringing in my vec from up top here. This obviously doesn't compile because we don't have capacity and length. So let's go ahead and create those real quick. Capacity takes in self and returns a usize here. This should be pretty easy. We can go ahead and just return the capacity field, and our length function is very much the same in that all we have to do is return back len, the len field. Cool. Great. This still complains because it can't actually infer the type for t. So for now, let's go ahead and do, and in fact, let us go ahead and, yeah, we can, I'm going to do, nah, let's not do that. Never mind. Forget about what I just said. We'll just give it an explicit type to say that it's going to be a my vec of usize here. And it's complaining that, it's marked as mute even though we're never using it mutably. That's fine. It will still run. And of course our assertions are completely wrong. This capacity should be 0 and this length should be 0. So if we run that, and let me go ahead and, terminal here, then everything is passing. Cool. And chat was asking, is it possible to do this syntax, which it is. Real quick, we can just go ahead and do usize like this. That might be nicer, so we can, oh, sorry, no, we can't. We can't do that. The reason is because new does not take a generic parameter. It's the type itself. So we can do this, usize. That works fine. And then we can get rid of this type annotation. But it's the type itself that takes the generic parameter, not the new function. So putting it here would be the generic parameter is on the new function itself, which it's not. Putting it here means my vec itself is takes a generic parameter. Cool. So this is all working. This is pretty straightforward. Hello, welcome. Hopefully this makes sense to everybody what's going on here. We're not actually doing anything that interesting, but now we're going to go ahead and implement the push function method real quick, and that's where things really get going. All right. So let's go ahead and do pub fn push, and it's going to take a mute self. And return nothing. All right. And the first thing that we said before was that we have an invariant already, and the invariant is that when capacity is 0, we have a dangling pointer. So we should probably first say, okay, if self.capacity, and we don't need to use the function, equals 0, then let's go ahead and initialize this thing first. So how can we go ahead and do that? How can we initialize and actually create a heap allocated piece of memory for use in our vector? Let's go back to the documentation here and take a look at the Alec module here. So standard Alec is a bunch of memory allocation utilities. And in fact, we have standard Alec here. We can go ahead and just straight use the Alec crate instead. For those that are not familiar, by default, every Rust program comes with the standard library, but you can opt out of that. And if you opt out of it, then you opt out of everything, including any heap usage whatsoever. But you can re-opt into heap usage through the Alec crate. And then you can use all of this stuff. And so we could effectively make myvec completely non-standard so that people who are just using the allocation crate but not standard itself would be able to use our vector. I don't think we're going to do that today, but that's an interesting exercise for the reader. Cool. So Chad is asking, how are you going to make one with dynamic size? I think what you're asking is how are we going to allocate dynamic memory, perhaps? And that's exactly what we're talking about right now, is allocating dynamic memory through these allocation functions. And in fact, if we look down here, the functions are really what we care about. And the first one is Alec here. So what Alec does is it takes a layout, which we'll talk about layout in just a second, and returns a mutable pointer to U8s, what essentially means it's returning back a pointer to bytes. The question in chat, you've got a capacity field. How are you going to change the size if it's not static? Yes, we're going to change capacity as we go along. As we allocate more memory, capacity will change. So capacity, and in fact, you can see here, we have a mutable reference to self. We're going to change capacity in this. We're not quite there yet, though. All right. So this is how we allocate memory, and you can read more about this, how this goes through the global Alec method. So when you're using the Alec trait, you can register an allocator because maybe you want to go ahead and use a different allocator than what comes by default. I think by default, the global allocator is kind of the system allocator for your system. So you can go ahead and, if you're on Linux, then it will use the Linux, the whatever allocator comes with your system that you're using. And you can change that if you want to use jmalloc, for instance, and opt into a different type of allocator. Then you go through this global allocator attribute, and then the Alec trait has actually implemented this global Alec, and we should look at this global Alec trait for that allocator, and so it will go through that and use the system allocator in order to allocate our memory. So last thing we need to understand about that is layout, and basically what layout is a piece of data that describes the layout and memory of what we want to go ahead and allocate. And so we can look at that real quick. Layout describes an instance or a block of memory. You basically build, as it says, you build up a layout as input to the allocator, and it describes the size and the alignment of your piece of memory. And there's a whole bunch of ways to allocate these things. I think we'll see that there's more than one way to get the right answer with layout. Layout is kind of very open for use, and we'll see how exactly we want to use it in just a second. So we know that we need to allocate some memory. We need to call standard, and let me go ahead and up here use standard Alec, so we can just call it Alec. So we want to call Alec with some layout of memory. So we need a layout, and we can call layout. And what do we want to do here? Well, we just like the standard vector, we want to allocate space for 4 items on the heap. Why 4? Because someone, I don't know, somewhere, hopefully, did some kind of reasonable guesstimation of what a good kind of first allocation for a vector is, and 4 was landed upon. Why 4? I'm not exactly sure. Why not 8? Who knows? It being a power of 2 is always good. A power of 2 means that you're probably always going to end up inside of a page boundary then in memory. But we're going to follow the same kind of first allocation and also allocate space for 4 of our items inside of it. And maybe, later on we can decide to change that instead. So layout comes with a really great kind of constructor function called array, I believe. And what array takes is the number of elements in this array. So we can just go ahead and say 4. And of course we need layout, and it's inside of Alec, so we can just say Alec layout. And let's go ahead and look at array real quick inside of layout to make sure that that's exactly what we want. So it creates a layout describing the record for a T, comma, and so an array of elements of type T, and n number of them, so whatever we passed in here. And it says that on arithmetic overflow, it returns a layout error. What it means is that if there's kind of too much, if you pass in an n that's too large, and it will overflow the size of that layout, because you're passing in n, and n gets multiplied by the size of t to describe the number of bytes that that this layout will take up. If that ends up overflowing, then this thing will return an error. And so what we can go ahead and do is just go ahead and say expect could not allocate. So we're going to take the easy way out for now. This is roughly what the standard library does. This push obviously doesn't return a result or anything like that. We could change that and return a result on any kind of allocation error, return back an error saying, hey, we couldn't allocate this. If you want to do something when there's, maybe there's no memory left or something like that, then you can do that. But for now, we'll mimic the standard library's behavior and just crash the program or panic the program when we can't allocate anymore. And then there's a question in chat. So what if we increase the capacity and there's no continuous memory available? Will layout take care of moving the whole piece of heap somewhere else? Well, we're allocating for the very first time here, right? So there's no moving anywhere else. We are, for the very first time, asking the allocator to give us a chunk of memory. And there's only really two things that can happen there. The allocator can say, I did it, here's a pointer to memory, or say, you're out of memory, I don't have, your system literally has no memory left, I can't give you any memory anymore. And we haven't done that yet, but we'll see that we'll actually end up panicking on when that happens. All right. So we have the hopefully proper layout. We probably want to provide t here so that it knows explicitly what t is, and we're not relying on any kind of type inference or something like that. And I imagine there wouldn't be enough type inference for this to work. So we're just going to go ahead and say we want an array of t explicitly here. And notice that we're passing in 4 here, not 4 times size of t, because the array does that arithmetic as we already described. It will decide how many bytes we actually need based on the size of the array and how big our t is. Cool. This is complaining, I believe, because it's so it's complaining because we're not returning the proper type. I'm going to go ahead and just write the to-do macro here to get some of it to shut up. This won't help in this case, but that's always nice at the end of a function that you're creating or a method that you're creating to put to-do at the end, which kind of hides some of the error messages that you don't necessarily care about right now. Cool. So what does Alec return to us again? It returns back a result, right? There we go. Oh, Alec, come on. Oh, it doesn't return back a result. So Alec returns back every single time a raw pointer. And so we're going to go ahead and get back our pointer. And we probably want to go ahead and cast that as a pointer to a t. So we know that this will be, it gives back a pointer to U8, which is fine. It's just giving us a pointer to bytes, but we know that Alec returns back like a properly sized and well-defined and well-aligned pointer to our chunk of memory, and our chunk of memory holds t's inside of it. So this is totally fine. It's still complaining because we're using unsafe without the unsafe keyword. One last thing that I think we'll go ahead, no, let's go ahead and do unsafe here. And in fact, we can just do this. So this acknowledges right here that Alec is unsafe, and we can read about the safety here. Well, we have to, let's go into Alec, and for safety, read about safety. So this function is unsafe because undefined behavior can result if the caller does not ensure that the layout has non-zero size. So we know layout does not have non-zero size because we're getting a layout from array and passing in a non-zero to it. An array, when you don't pass in 0, will give you back a layout with a size bigger than 0. Assuming that t that you pass to array is also non-zero size. So let me just explain that one more time. Alec expects that layout is describing a piece of memory that's bigger than 0 bytes. And we are guaranteeing that doesn't happen. In fact, let's go ahead and write this here and say safety. The layout is hard coded to be 4 times size of t. Now this is a very good question, the first question that I've not thought of before. If t here is 0 size, then what will happen? So if we pass in, for instance, as t unit, then unit size is 0. And so we end up with a layout here that describes no memory. And Alec explicitly says that that's not okay. Let us, for now, punt on that and say this is curious. I'm wondering exactly what vec does here. Let's see if we can find this in raw vec. And I believe, let me go ahead and bump this up here. And of course I'm using GitHub's new dark mode here, which is what everybody is raving about. Let's see, inside of vec push. So it will call reserve. And this calls reserve on raw vec. And this calls try reserve. And this needs to grow. I'm wondering if that perhaps, nope, that doesn't care about 0 size types. At least I believe. So grow amortized. Oh, and grow amortized, this is not. Interesting, grow amortized. Okay, there we go. So if mem size of t equals 0, they. Interesting. So what they're doing here is when probably, I'm guessing, on instantiation, perhaps. Is there an fn new? Interesting. Somewhere they are, when the t that's being passed in is 0 size, they put the capacity at infinite, basically at u size max. And interesting. So we can go ahead for now. I'm just going to do this. If size of, we got to do standard mem. We're just going to punt on this for right now. We're going to ask if t, if its size in memory is 0, then we're going to panic. No 0 size types. And now we can say, and size of t is greater than 0. Cool. Yeah, and chat is saying, why don't I just use assert? Assert not equal mem standard mem size of t here. No zero-sized types. Any questions about this? Why we're doing this here? This basically just eliminates one of the invariants that we have to hold up. We know that t is not zero-sized. It has to have a size in memory. All right. So now this is good. We have our safety invariant. We're meeting it. The layout is hard-coded to be 4 times size of t, and size of t is definitely greater than 0. And so we have met that invariant, which means we should be good now. We've got we have a mutable pointer to t. Now, Alec, if we go back here and read about Alec, here we say returning a null pointer indicates that either memory is exhausted or layout does not meet this allocator size or alignment constraints. And so we can get an error if Alec returns to us a null pointer, but luckily we are modeling our pointer as a non-null pointer here. And so what we can do is just wrap our pointer, and let me go ahead and do that and say let pointer. So I'm shadowing pointer here and just saying that it's going to be equal to non-null new pointer. So this returns back an optional non-null. And it first checks and says, okay, is the pointer null? If so, return none. And if it's not null, then go ahead and return back the non-null pointer, which gives us a very easy way to check whether our pointer was null. And we can just go ahead and, like everything else we're doing so far, crash if it doesn't meet our expectations. So if we get back a null pointer from allocating memory, we'll panic with could not allocate memory. Oops. Any questions about this? Great. So looks like everybody's on the same page here. We now have a non-null t. That means we've got a really initialized pointer to a t, and so far the invariant that we now hold on to is that well initialized pointer actually points to a heap allocation of size 4 times the size of t. All right. And so we can go ahead now and say self.pointer equals pointer here. And then we can say self.capacity equals 4. And of course, we have to update len to be 1. All right. So we've set pointer, we've set capacity to 4 because we've allocated enough space for 4 things, and we set len to be equal to 1. And we can go ahead and get rid of our to-do here. And we should be able to push one item onto vec. What is it complaining about here? Oh, of course, we're not done. We don't take an item actually here. So great, we've allocated memory. That's not actually what we want to do. I mean, it is what we want to do. We want to allocate memory, but we also want to write to that memory. We now have enough space on the heap for our items, but there's nothing there. We need to write our item to that space. And so in order to do that, what we can do is pointer, and this is kind of weird, pointer as pointer. So we're taking the non-null pointer and turning it back into a raw pointer real quick. And then we can call write on it and give it our item. And we have to wrap that in unsafe as well. And we probably want to go ahead and write some safety tips here, why this is okay. So pointer is non-null, that's good. And we have just allocated enough space for this item. And 3 null. So let's take a look at pointer right real quick to see any more invariants that are written down there. So we can go to pointer right. Pointer right says it overwrites memory location with a given value without reading or dropping the old values. So it's not going to, so we're writing to destination here. What we want to make sure of is that we don't read destination because it's completely, uninitialized. And so if we end up like reading destination and putting it onto the stack, for instance, and then it gets dropped or something like that, we would end up running the destructor for t when t is actually uninitialized, and that's undefined behavior. That's not good. We don't want to do that. So this is appropriate for initializing uninitialized memory, which is exactly what we want. Or overriding memory that's previously been read. So we've read a value. We don't want to go ahead and read it ever again. We've already read it. We already have a known value. If we were to read it again, we would end up possibly with a double free, which we don't want to do. Chad is asking about if I added a format debug implementation. We have not added debug yet, but we can certainly go ahead and do that. But we'll leave that for the end. So this seems to be good. Like, now you might be wondering, like, you know, why write and not something like this? Pointer as pointer. What if we did this instead? And I believe this is incorrect because this ends up reading the value at pointer. So when we go ahead and use this kind of star assignment syntax, to go ahead and assign to a raw pointer here, we will actually end up reading the pointer, which is exactly what we don't want to do. So this is out of the question. We don't want to do this. We want to do this instead. And we can say here the memory previously at pointer is not read. Any questions about this? Any questions about the invariance that we're trying to uphold here? Now, this code might not yet be fully correct. We're going to talk about that. Oh, we can talk about that now. We can talk about that now. A big thing that we have to worry about with unsafe code is panic safety as well, to make sure that if our code panics, that we're always in a good state. And so, for instance, if we go ahead and panic on this assert not equal here, is our vector in a state that does not allow for any of its memory safety invariants to be violated? And the answer is right here, everything is good. If we panic right here, our length and our capacity is going to be set to what they should be set, and we're not going to allow any outsiders to read from memory except for the memory that is fully initialized in our vector. So that's fine. Same thing with layout here. We haven't really done anything to change our vector, so we're fine. And same thing with non-null here. If we panic right here after we've allocated, we know that we would only panic if pointer returned null to us, and presumably it would only return null to us if that memory was not actually allocated. And so, you know, there's no chance even here of leaking memory or anything like that. So pointer as pointer right, that can that even panic? It doesn't look like it can panic, or it doesn't, at least is not documented as being able to panic. So this should be fine as well. Now it's an interesting thing. Are we, you know, we first set pointer here and then capacity and then length. Is this fine to do in this order? We should be fine because nothing should panic in here, to where we've set the pointer and then there's a panic here where the pointer is set but the capacity is still wrong, or vice versa. So this should be fine as well. So we should also be panic safe. We could panic in any place that is where it is possible to panic in this code, and no invariance will be violated. Chat is saying more cases needed. In general, you must offset the pointer into the right position. So pointer is always going to be pointing to the beginning of our vector. So we don't need to offset the pointer. In this case, we're simply allocating the pointer, setting it to the beginning of our memory allocation, and then our length and our capacity are what set the bounds of where our memory is initialized and the bounds of where our memory is actually allocated. And then you're saying this is push, not new with val. Can you explain what you mean with that? I'm not exactly sure. If you let me know what you mean, then I believe this is correct. But if it's 100% possible that I've written something that is completely wrong. While chat figures out what the issue is, we can go on. Now we've only handled the case where capacity is 0. Obviously, if we push more items onto our vector, they'll simply be dropped. Are you saying we're not handling the case where capacity is not 0? That's totally true. Like we have more to do here. Else to do. This is probably more correct. Yeah, absolutely. We're not done. We're definitely not done. We are done though with the capacity equals 0 case for sure. Cool. So now we need, there's basically 2 cases left as far as I can tell. There's the case where we're pushing an item, the capacity is not 0, but the capacity is enough to push on a new item. So for instance, we push one item onto our vector, the capacity goes up all the way to 4, but the length is 1, right? We've only pushed one item, but we've allocated enough space for 4. When we go ahead and push another item onto our vector, we don't need to allocate any more memory. Enough memory has been allocated. We simply need to write that value into the right slot in our allocated memory, and then bump up length, and that's it. So basically what we can check for here is if self.len is less than or equal to self.capacity. And then we can go ahead and keep our else case here with a to-do. So this is the case where the length of our vector is less than the space that we have for it. And I think this is strictly less than. Yeah, if we have a capacity 4 and a length of 4, that means we've filled up our entire vector so far. So we strictly want to look for is the length less than the capacity of our vector. And in this case, all that we need to do is to go ahead and write our item to the pointer, or to our memory allocation at the right spot. So this is definitely going to be unsafe. And what we can do is say self.pointer. We know that pointer is correctly is pointing at good memory. We've done that. We've checked that in the capacity case. Once capacity is no longer 0, we know we are keeping the invariant on ourself, that self.pointer is always pointing to valid memory. And what we can do is turn that non-null pointer into a raw pointer and then call offset on it. Or actually, we'll just call add. And what add does is it calculates the offset from a pointer. And it's important to note here that count is in units of t. So if we pass in 1, we are going to not skip ahead 1 byte, but rather 1 times the size of t in bytes. So if t is 10 bytes big, or 12 bytes big, let's say, we'll skip ahead 12 bytes from our pointer. So where do we want to skip ahead to? Well, we want to skip ahead to self.len here. So imagine the length is 1, for instance. We have our pointer. We have 1 element in there. And so we jump ahead 1 element into the array, and now we're pointing at the first uninitialized item in our allocated memory. And here, then we can call write again and pass an item. And then all we need to do now is update len to go ahead and update len to be plus equals 1. Now I think this code is mostly good. Now we don't need to update capacity, right? We haven't allocated any new memory or anything like that, so capacity stays the same. This code is mostly good. There is one case though that we're not handling that could go horribly wrong. Well, let's read safety real quick to make sure that we're doing this. So both the starting and resulting pointer must be either in bounds or 1 byte past the end of the same allocated object, which is good. So we have our allocated heap memory, and we know that even if len is less than capacity, we can point up all the way to the end of our allocated memory. This is an interesting one. The computed offset in bytes cannot overflow an I size. This is interesting. So think about this. When len becomes very large, let's say it's millions or whatever, billions, we have a huge vector. And let's say we're storing t's that are also, I don't know, 128 bytes big or something like that. It could be conceivable that multiplying our length times the size of the item that we're storing actually causes the computed offset to wrap around. And that is a bug for sure. So we can go ahead. Yeah, so and also the offset being in bounds cannot rely on wrapping around the address space as well. And what will happen? We'll segfault, but if, again, we're creating a safe Rust wrapper, we cannot segfault. That is, and in fact, you know, what will happen is most likely it will segfault, but it's not guaranteed. We're actually in the realm of undefined behavior here, so what will happen is we don't really know. Probably will segfault, but we don't know. And we can't rely on that behavior at all. So what do we need to do here? Well, we could do something like assert self.len times self.len times size of t is less than I size max. We gotta wrap this in parentheses here. Oh, but this could also overflow. We could then do, instead of asserting here, we can do self.len checked mul. So we're going to do a multiplication here, and what checked mul does is return back, as you can see here, as you cannot see here because I'm missing a semicolon. So you can see here, is there no checked mul on usize? Usize, check mul. Did I spell it wrong? Check mul. Yes, I did spell it wrong. Cool. So we're going to do this multiplication here. It returns back an option usize, and we can once again go ahead and panic in this case. So effectively, like we now, I don't think this is possible because, and I'd have to do some thinking about this, and I want to get the point across here that like writing unsafe requires a lot of thought. And the nice thing about Rust having the unsafe keyword is that at least when you write unsafe, you have to like go through the checklist and see every single thing that could go wrong. I'm not necessarily convinced that this check is strictly necessary because I'm not sure len can get big enough for us to get into this situation. But I'm going to leave it in here for now because this is definitely, while it might be wrong, it's definitely safe. And leaving it out might be right, but it also might be unsafe. So let's stay on the safe side here, and we can work on later convincing ourselves that this check is actually not necessary. But I think that this satisfies all the safety requirements that we have. So we know that offset cannot wrap around. And pointer is initialized. Pointer is pointing to valid memory. And writing to an offset at self.len is valid. It's supposed to be less than I size and bytes. That's true. I think this also works. Truncating, so when you convert a U size to an I size, this itself might wrap around as well, I believe. This is why I don't like using as conversions, because it's kind of hard to remember exactly what happens when you convert in a lossy way. So I'm trying to see here if we look for or in fact, if we look at I size and look at try from U size, this I believe yeah. I think what we can do here is let's do this. This might not be the most efficient way. There might be a way that's a lot more efficient than this, but this is the easiest one for me to remember, or for me to implement right now while everybody's staring at me, is we know that this offset in the usize space has not overflowed, and then we can check that assert that offset is less than this should work. So we do the multiplication in the usize space, and then we check that the usize that we get back is not larger than the maximum I size that we have. There's definitely a better way to do it than this, but this definitely works. So we'll leave it at that. All right. So I'm fairly convinced that we're in a good place here, that we have handled the point where we that capacity is 0, where length is less than capacity, and the final thing that we need to handle now is where there is not enough capacity, this else case here. So here we need to essentially reallocate memory and get more of it. And luckily what we have inside of Alec here is realloc. And what realloc allows us to do is take in a pointer and reallocate it with a new size that we have. We can read about realloc here. So it can shrink or grow a block of memory to the new size. And the block of memory is described by pointer and layout that we pass to it. The layout here, so it says, if this returns a null known pointer, then ownership of the memory block referenced by pointer has been transferred to this allocator. Now, importantly, this means either, it might mean that the previous memory was completely deallocated and that the memory allocator has kind of moved this entire thing somewhere else, or it can simply say, hey, there was some space after here, and I'll just go ahead and allocate that space to you. So it makes no assumptions about whether the pointer that we get back is the same pointer or not that we had that we passed in, and we can't make any assumptions about that either. And we know that if the method returns null, then the ownership has not been transferred to this allocator, and the contents of the memory block are unaltered. But obviously, it has not reallocated that memory, so we're kind of dead in the water then. And this is important. Like, pointer must be currently allocated via the allocator, so we should be good there. Layout must be the same layout that was used to allocate that block of memory. New size must be greater than 0, and new size, when rounded up to the nearest multiple of layout at a line, must not overflow. Blah, blah, blah. So essentially, new size here, it cannot it cannot overwrap. Of course, it's a little bit bigger than new size, potentially, if new size returns back a number that is not a multiple of the alignment of the type. It will check against the alignment of the type. So we need to do that as well. So let's go ahead and get into this. We'll go ahead and say unsafe. And then we have Alec, reAlloc, and we need to pass in the pointer, so it's self.pointer as pointer. It's going from the non-null pointer to a raw pointer, which is what reAlloc expects. Then we need to pass in layout here, and layout is going to be equal to, and I believe what we can do here is layout from size align unchecked. This needs to go inside of the unsafe block. Let's look at from size align unchecked on layout here, because this is another unsafe so from size align unchecked takes in a size and an align. It doesn't do any checks. Safety, yes. So the function is unsafe as does not verify the preconditions from size align. So as long as we meet these conditions and we know that we meet them, we can call this, and we don't need from size align to do the check for us. So the align must not be 0. We're going to call align on, we're going to call stand mem align t, and we know t is not 0 sized, and so align must be non-zero. And in fact, I think even 0 size types have an alignment that's non-zero. Align must be a power of 2. Stand mem align of, will it, this is an interesting one. Align must be a power of 2. I guess 1 is a power of 2, right? Yeah. Because 2 to the 0th is 1. So anything that we get back from stand mem align should be a power of 2. That's fine. And size, when rounded up to the nearest multiple of align, must not overflow. This is going to be the hardest one to check. But let's go ahead and call this here. We're going to pass in stood mem size of, and I'm off the edge here. I hope everybody can see this. We're going to pass in stood mem size of t, and for align, this is stood mem align of t. I don't know if we talked about alignment. If you're not familiar with alignment, what alignment is that every type has a place, has memory addresses where it needs to be, because the processor expects certain chunks of memory to be at certain offsets in memory. And so if you have a type that has an alignment of 2, for instance, it must always start at a memory address that is a power of, that can be divided evenly by 2. If you have a type that has an alignment of 16, then that means if you that type must always be at a memory address that is evenly divisible by 16. And this std mem of what it just returns back is what the alignment of our type is. And so whatever t's alignment is, we'll get that back here. So this should be fine. The only thing that we're not accounting for here, because a line will not be 0 and a line will be a power of 2, size cannot overflow when rounded up to the nearest multiple of a line. This is an interesting one, and given our non-success of that we had before, and this is wrong too, because this is the size of memory, which is not std_mem size of t, but rather std_mem size of t times self.capacity here. So really what we need to do here, and this is always, I'm always the worst at arithmetic, so it's the thing that I struggle with the most. This is size. And what we need to verify here then is that size, and then we need to, what was it? We need to round up to the nearest multiple of a line. What is the easiest way to do that? We need to make sure that when we add something to size that and take the modulo of a line, that it ends up being 0. So we'll need a line here as well. There's a question in here that I tried to make clear at the beginning, but it demands being said again. Why are we building a custom type, a custom vec, if you can get it from GitHub? Do not do this in real code. This is purely a learning exercise. Never use this code. I will publish it to GitHub with a big old indicator saying, do never ever use this. This is purely for learning. Now, the lessons that we're learning here should hopefully be applicable to other situations where you don't have a ready-made safe type like vec. But this is totally just a learning exercise. Completely just a learning exercise. Cool, so let align is this. And so now what we, is there a there's not like a round 2 or something like that can take care of this. So we need to checked add size modulo align. Oops. I believe this should do it, right? If our size is 10 and the alignment is 4, then 10 modulo 4 is 2. And when we add 2 to 10, we get 12, which is a multiple of a line. like I said, I'm really bad about these types of things, especially when people are watching me. So chat, check my homework there to make sure that my thinking is correct. Assuming my thinking is correct, then we can just go ahead and do this and say, because we have wrapped around trying to get new memory. Chat is wanting us to note the interesting relationship between physical memory addresses that the processor can load from and virtual addresses that the OS allocator hands us. Yes. So in a sense, the OS allocator, or the allocator, it doesn't even have to be an OS allocator, the allocator is passing the buck to us to make sure that we are always dealing, I mean, it's not passing the buck, it helps us with this, but make sure that we're always dealing with memory addresses that have correct alignment, so that it can very easily kind of pass those over and translate them over into physical addresses, because it's really just the processor at the end of the day that really cares about this. Cool. What is this complaining about? Oh yeah, takes a line as well. So I'm 90% confident that we're doing things right here, that we are checking all the invariants that we need to. We're passing in the correct layout, and the last thing that we need to pass in is the new size. So let new size here. And new size here should be in bytes, because what we're doing is dealing with bytes here. What new size is going to be stood mem size of t here times whatever new capacity that we have. And so we want to up here say new capacity is going to be equal to self.capacity times 2. And just to make sure, let's go ahead and do checked mul here as well, that our new capacity doesn't wrap around, because I don't want to even have to think about what could go wrong if capacity wraps around. Now, just to reiterate, a lot of these expects are not necessarily necessary. So homework to you is to go through the expects, make sure that we're doing the right thing, but also it's potentially possible to remove some of them, because we won't actually end up, we're not actually saving ourselves from violating any memory invariants that we might have. This is us being very cautious about how things are going. All right. So realloc gives us back a pointer. And what does this complain about? Oh yeah, that it expects the pointer as not as a raw pointer to t, but rather a raw pointer to u8. Oh, nice. I'm gonna make this a tiny, is it okay if I make this just like a tiny smudge bigger? I hope that's fine. Cool. So now we have potentially reallocated memory. Realloc will take care of, if it does get new memory, it will move the memory that we previously had over to the over to the new memory allocation that it's creating. And so we really need to just check the pointer here and make sure that it's non-null. So we can go ahead and say non-null new, not any, new, and pass in pointer as pointer to t here. And again, if we can't realloc, we'll just go ahead and explode. Could not reallocate Now, this is interesting though. If we go back to the documentation on realloc here, and inside of here, then if the method returns null, then the ownership of the memory block has not been transferred. So let's assume that that calling realloc returns null. We will panic in that case here. And is that fine? That should be fine. We won't leak memory. We will panic. Currently we will leak memory, but we still have not implemented the drop trait on this. So, but we should be in a good state because we haven't updated capacity and we haven't updated length. We haven't updated pointer. The pointer that we passed in here is still valid in that case. The capacity is correct. The length is correct. So we should be totally fine to panic here. Totally cool. Great. Now, if we didn't panic here, we know that we have successfully reallocated memory and we now have a new pointer. And so we should be able to say, well, first thing we need to do is go ahead and do pointer as pointer right. And then, sorry, not right. First, we need to add self.len. Yeah. Self.len, just like we did before. And we're going to write an item here. So this is fine. So we've now written at length here. We probably want to debug assert here that self.len equals self.capacity, right? If we reach this case, we should never, ever, ever have len be more than capacity. We've already checked the case where len is less than capacity. And so in this case, we should always have len equal to capacity. And I'm doing debug assert here because unless we've made a bug in our implementation, debug assert is fine. Debug assert will only assert on and debug builds. And release builds, it will just that code will just fade away. All right. So we've written our item here. Importantly, there's probably the same check that we did up here. We should do down here, but I believe that these checks here that we've done in order to reallocate the memory means that we don't need to redo the check here. So we should be fine. Again, let me know if you think that that's wrong, but our check that we did up here should be met no matter what when we get here because of the checks that we did up here. So we've written our new item at length offset, and then we can do self.pointer equals pointer, self.len equals is plus equal 1, and self.capacity is equal to new capacity. And in fact, we can move this out of the unsafe block. Now I am curious if self.len plus equals 1 is guaranteed to always work. If this overflows, which should not be possible because we have checked that we have enough capacity, that capacity doesn't overflow, and if len is equal to capacity, then we've also checked that len won't overflow when doubled, and so adding 1 shouldn't double. So this should be fine to do this. it's important to really think about whether things can panic, for instance, because if we were to panic right here without capacity set to the new capacity, I think that would be fine, but we would leak memory for sure in our drop implementation, which we've not yet done. And in fact, drop is not necessary because all that drop is going to do is free the memory, but that's fine. Like, we don't need free memory. There's nothing about memory safety that says you can't have memory leaks. And so this here should work now, I want to say. So what is our capacity going to be? It should be 8, and our length should be 5 here. Let's run this. And hopefully my computer does not explode. Awesome. Now we could check with Valgrind to see how we're doing with memory allocations. So I'm going to do cargo build -- release, and I never remember Valgrind how it works, but I want to say we should just be able to do like this: target release. Where is my target release? Oh yeah, we are building a library here. We could run Valgrind on our test binary as well. The thing with that is I always worry about the test harness kind of muddying up the output and stuff like that. So what you can do instead here is just create a binary like this. And I'm just going to go ahead and steal our test here. Oops. And I want to say that we need to do, what do we call this thing? MyVec. And this should be fine. And now if we do cargo build bin release, sorry, I gotta pass in. Oops. Pass in the name of the binary here, and that should give us this. Yeah, there it is, MyVec, a nice executable for us to use. That only has this code. Again, we could have used the test code. I think that's inside of deps, I want to say. So target, let's look at debug real quick. Debug deps. This right here is the binary for our tests, but it also includes the test runner and all of the code that gets bundled in when you actually run tests that prints out, test pass and stuff like that. And that's a lot of extra noise. So we just got a plain binary now that we can work with, and we can call Valgrind on. Valgrind is a great tool for looking at memory allocations and learning more about them. And so target release MyVec. So we have leaked memory, which is fine. We had 11 allocations with 10 frees. The 10 allocations that were freed, I would imagine, are coming from the from Rust, kind of the Rust runtime, the initialization that happens, which is basically the C runtime. And the 11th allocation that was not freed is our allocation that we made. Although it's interesting. No, it is free. So, sorry, 9 of them are probably from the Rust runtime, because we've done 2 allocations, remember, right? We've done allocation right here and allocation right here. We've done alloc and realloc. But when we reallocated, potentially, And this might not be the case. It might be that that the allocator simply increased the size of our, and in fact it probably was this. The allocator just took the allocation that we had before, and it probably behind the scenes like has a whole memory page that it has at its disposal and kind of marked for our use, but only said like, hey, you can only use this first part. And when we reallocated, it just said, okay, like you can have a little bit more of that page that I allocated for you. That's most likely what happened behind the scenes. So we're definitely leaking memory. And in fact, I think we can use this right here. Go away. You're not fun. What did I... Oh, and I think I have to do this before. Oh, that's annoying. We're running with leak check full here. Let's see, did it? No. To get even more information about... yeah, so it's going to give us a... Let's close this. Give us a little bit of a stack trace here to look at. And you can see in realloc here, which is the libc realloc, we are that was where we actually allocated. That was lost. We never deallocated the memory that we got from realloc. So very, very useful information, very obvious in this case, but Valgrind is great for weaning this information when you don't necessarily have it at your disposal. All right, so how can we go ahead and fix that? Well, let's go ahead and implement drop. And drop, of course, is what gets run when our type gets dropped. myvec ot, and of course we need this to be t. Not of, for. Oh, and there's a new question that we've already answered, but I am happy to repeat this once again for sure, because this is, I am writing my own vec for educational purposes. Do not use this code. Do not write this code. Take this and use it where you don't have. No worries. Totally get it. No, it was already asked. And I'm always happy to repeat it because like I don't want anybody to get the impression that implementing your own vector is a good idea, because it's not. That the reason for that is because the standard libraries vector is very good. So there's really no reason to implement your own, other than for educational purposes. But a lot of this, I just want to repeat again, a lot of this information can be used in situations where you need to dip down into unsafe goodness, not to build your own vec, but for some other data structure or something like that. It does happen every once in a while, particularly in very advanced use cases. And so this is probably good knowledge to know. All right, so we're going to implement drop here. We've done our best to try and make sure here that if we enter into drop here, that we're in a good state. So it's up to this code up here, the unsafe code here, to make sure that when we get drop here, that everything is in a good state. So what we need to do is first drop all of the items in our vector. So our vector itself has memory that it's allocated heap memory, but there's also items in that heap allocation that might themselves have other heap allocations. Let's imagine a vector of strings, for instance, a vector of owned strings. You have the heap allocation that we allocated for our vector, and then each of those are strings which have pointers inside of them to other heap allocations, and we need to signal to those strings for them to that they're okay to be freed, for them to run their own drop implementations. And there's a great way to do that with standard pointer drop in place. And if we look at drop in place here, So this executes the destructor of any of the pointed to value. It's, as it says, it's semantically equivalent to calling pointer read and then discarding the result. But it has some advantages over that. It can work with unsized types because unsized types cannot be read to the stack. And it simply doesn't need to bring those items onto the stack. So it's friendlier to the optimizer. It doesn't need to prove anything that it's safe to ally copying those values to the stack. Because the optimizer will try and say, you don't actually need to copy these to the stack. If you use drop and place, it means you definitely don't need to. So let's look at our safety rules here. So it's undefined if any of these conditions are violated. To drop must be valid for both reads and writes. Okay. To drop must be properly aligned. That should be fine. And the value to drop points to must be valid for dropping, which we should be fine here. And there's kind of a cheater way that we can go ahead and do this that I think just because we're reaching the end now, I'm going to go ahead and do. There's a question in chat: is this only good for own types? No, we're going to call drop on if T happens to be borrowed, we will drop the borrowed values, and dropping a borrow does essentially nothing. It doesn't call drop on the thing that the borrow is referring to. It simply just goes away. So this should work fine for everything. So what we should be able to do is to call stood slice from raw parts mut here. And I said I wasn't going to use slice here, but this is the cheating part here. We're gonna use slice in this case. I guess the other way to do it is iterate through and drop each item one by one. So we're going to turn our pointer and our length into a slice, and that slice will then be dropped. So all we need to do here is self.pointer.asPointer, and len is self.len. And this needs to be inside of unsafe, like this. So with this call, we are effectively dropping all of the items in our vector, which is half the battle. Now what we need to do is deallocate our heap allocated memory, the heap allocated memory just for my vec. And as you probably imagined, inside of the Alec module in here, down below, there is dealloc right here. And dealloc does what you would expect. It goes ahead and deallocates the memory according to the layout that we have. So we can just call Alec dealloc, passing in self.pointer as pointer here. And we can pass in a layout here, let layout. And this, we can just use our old friend from before, layout from size, align, unchecked. And these should all be fine. We've kind of already done the check in push to make sure that that we're not going to violate any of these invariants. So this is going to be the size is stoodmin size of T times self.capacity, like this. And sorry that this is really not, make it one size smaller. Hopefully you can still see this. This is not formatting as I would hope it would. Hopefully in just a second it does. And the align is going to be std mem align of t. And there we go. And what's it complaining about here? Oh yeah, we're passing in a raw pointer to a t, but it just wants a raw pointer to bytes. We can do this. Oh, not t. Casting raw pointers also works like this. You can just say, figure it out. Cast to whatever you need. That's fine. I like leaving it like this, just so everybody knows what we're doing, and there's not any kind of magic there. And so now we should be good. We're dropping all of the elements in place, and then after we're done with that, we go ahead and call dealloc to deallocate the memory that we have specifically allocated for myvec. So if we go ahead and open this back up, let's run valgrind once again and see if valgrind is happier with us. So we can do build. So we've built the myvec binary, and then we can run valgrind again. Hey, and everything looks good. We have 11 allocations and 11 frees, and it doesn't look like we've leaked any memory whatsoever. And this is interesting too. It says that 2073 bytes were allocated. Let us inside of here replace this, not with the standard library vector instead, and go ahead and build that, and then run. And it looks like it's also allocated 2073 bytes. So we are, from a memory perspective, at least for this example, just as memory efficient as the standard library's vect implementation, which is good. All right, we're coming to the end here. Just to make sure that our vector actually works as we expect, we're going to go ahead and implement git here. And what git does is it takes an index and returns back an optional reference to t. So how do we go ahead and implement this? Well, the first thing we need to do is check that index is good, right? So if index is greater than or equal to self.len, then return none. This is the case where we're out of bounds, essentially. And now we don't have to worry about the out of bounds case. Now what we can simply do is do self. We need this in unsafe because we're going to be reading from our pointer, a raw pointer. Whoops, unsafe. Self dot pointer. Let's scroll down here. As pointer. Add the index, and then we should be able to read and borrow here. And we need to wrap all this in sum. And what's it complaining about here? So this is, what this is returning to us is a pointer to t, right? So we need to first dereference that and then get a reference to it, like this. And what's it complaining about here? Oh. T cannot be dereferenced. Ah. This is returning back a T here. So this is actually not what we want here. It's, we're reading the pointer and actually getting the value, getting ownership of the value. So I think what we'll do instead is just, instead of using read, this should be fine. Here, we're just getting the raw pointer from add, then dereferencing it and getting getting reference from that. So if we go ahead and run cargo run, everything looks good, but we should probably in here assert equal that vec.get, let's get the third item here, should be sum 3. Cargo run. Ooh. Oh, and of course it's not 3. This is 0, 1, 2, 3. So this should actually be 4. And there we go. And in fact, what we could do is for n 0 dot vec dot len here, we can go ahead and get n here and check that it is equal to n plus 1. And that works. Oh my gosh, thank you, chat. You are right. We were using vector before. Okay, all right, good. So we just verified that standard vec works, which is good. It would be very surprising if we found a bug in standard vec in this very small exercise, but we've also confirmed that my vec also works, which is good. Now I'm interested to see, just to make sure, like structs drops, and if we implement drop for this funky little drop struct here, and just say print line dropping. And instead of this being a my vec of usize, we said this is my vec of dropped. And we just pass in dropped here. Well, let's do 2 of them. Why not? Just complaining about here. Too many P's. And we go ahead and print end of main here. And let's do vec.get 1. Let's go ahead and assert eq here that this should be some dropped, and I guess we'll have to implement partial eq here so we can compare. What is it complaining about now? Debug also, whoops. In order to use assert, it has to be debug. And what I want to test here is that we should push these on, get 1, everything's fine. And then here we print end of main and then we should see drop-in twice after end of main. If we see it before, then this is a zero size struct. Good point. Let's go ahead and throw a usize in there. And then this should be, yeah. So this should work. What? Looks like we've got a bug then. This is right. Or maybe, of course. This capacity is now 4 and the length is 2. And we do have a bug. All right. We are calling drop-in probably inside of Git here. And notice here, like this is memory. We have a memory safety issue, and the reason is we are not upholding an invariant here. So let us say, no, this is fine. No, let's go back. Whoops. Save here. What did I do? I screwed this up. Yeah. Let's go into Git here. Just got. I'm going to get. And my assumption is that we shall see going to get drop-in just got. Going to get drop-in just got. Exactly. So we have the same issue that we talked about before, where when we dereference the pointer here, we're actually reading T instead of and we're reading T and it's like being put on the stack and then we're dropping it at the end. So we get a reference to it and then, but we're also dropping it. The correct solution to this, can we do, oops. And unfortunately we can't do this. Where we cast first to a constant pointer and then cast to a reference. And now I'm forgetting exactly what the right way to solve this is. We want to turn the value into a reference without dropping it. Oops. And we can't do that here because if we dereference this pointer, then it will end up being dropped, which is exactly what we don't want. That's a good question. Chat, any ideas what we might do in order to fix this bug? there's been, I think, several discussions about this, about how to create a raw reference, so like a reference from a raw pointer directly without running into these issues. We can go to Google here and see raw pointer to reference without dropping. We don't want to modify it, we want to read it. And unfortunately, I'm not exactly sure what the best way to solve this issue is. So we'll leave this as homework for everyone. And it shouldn't be too hard. But the goal here is to fix this bug that we have. Oh, you know what? You are totally right. You are totally right. It's not a bug. We're doing the right thing. Thank you. I was losing my mind there, thinking there is no way if we do this, we should now see the right thing. Oops. Got to go back to boom. And gotta make the reference here. Yeah, okay. Creating a temporary. Takes a lot to prove that we're doing the right thing here. Third dropped. You are totally right here. There we go. You're right. Thank you very much. Oh. Whew. So that is one last lesson about unsafe, is that it can be a real doozy there. All right. Well, that's all I have for you today. We went a bit longer actually than I was hoping to, but we fixed all the bugs. We've got it working. I can go ahead and push this up to GitHub for everybody to take a look at. As long as there are no remaining questions, this will be up on YouTube afterwards. I hope everybody enjoyed it. Again, don't use this code. Don't implement VEC on your own, except as a learning exercise like we did here. Please let me know what you thought. Make sure to subscribe on Twitch if you can. That really helps me. Also on YouTube and Twitter that you can find me. I'm at Ryan_Levick on Twitter. And hopefully we'll be doing this soon. I'll probably be back next week with a new beginner-friendly tutorial since this was more of an advanced one. So thank you very much. I appreciate everybody's time, and I hope everybody has a good weekend then. All right, thank you.